me. I'm located out on the West Coast. Right now I have a group of my fellow consultant engineer specialists. We'll go right around, and we're all here for any questions that you may have. I got Diksha. She's located out in the Midwest. I have Matthew Wickham. He is on the East Coast. Robert Angst is East Coast, Southeast Coast, Southeast. And I have Richard Purcell, who does the
Atlanta, yes, Southeast.
So today we're going to give you a quick overview of breaker basics. I'm not sure what level of competencies you guys have on breakers, but we're just going to talk about how breakers work and what they're used for in their application. We hope that you guys have any questions. Please feel free to write in on the question pane. I will get to it as soon as I can. We'll probably have a Q&A, live Q&A at the very end. And hopefully I'll have all these smart guys with me to help me along as we go through this presentation. So I think you guys are still coming in. It looks like we got about 300 people. So I'll start it off. Okay, so breaker basics. I'm not sure if everybody knows what a breaker is. So we're going to cover the product fundamentals, the applications that we use them on, and the electrical standards. A circuit breaker is a device that is designed to open and close a circuit using a non-automatic, which is a manual means. As you can see, most circuit breakers have switches on them, so you can walk up to the actual breaker, flip a switch, and you're basically disconnecting power to all devices down the line from that breaker. It also has the ability to trip or automatically open the circuit based on overcurrent levels without injury of anybody being around. So if you have any kind of short or an overload, and we'll talk about the different types of faults that you may see down line, this breaker is there for safety for both the person and the equipment, where it will open up and make sure that all power is disconnected and service can be done down the line from the breaker. Basic parts of the breakers, as you can see, we have an operating level right here. This is your manual on-off switch. A nameplate you'll find on all breakers, basically giving you the current ratings and all the rate voltage ratings that you have on the device, so you know exactly what you're looking at. Terminals are usually where the power comes in and the power goes out to down your line devices. An arc chamber, now one of the things that we know is that when you open up a current switch or a breaker, you do have an arc going between the two contacts. We have moving contacts and fixed contacts. As you open up, you will experience an arc flash. We do take that into account, and we have these arc chambers that are designed specifically to make sure that the arc flash is extinguished as quickly as possible without any damage to our breaker. And finally, we have our trip unit, which you can think of as the brains of the unit. This allows you to set your trip curves, your trip levels, your current levels, time delays, and all other parameters that you want to put in the breaker. Basic ratings that you'll see on breakers are the current, which is usually referred to as frame size. There are various frame sizes that you can have. Continuous rated current, that means that's the current that can go through the breaker without causing any problems to the breaker or to the load. Basically what size of load that you're having, such as 800 amps, 1,000 amps, or what have you. 2,000 amps is usually the maximum that you're going to see. And then a maximum interrupting rating. This is basically the most current that this breaker is going to allow onto itself before it opens up and makes sure that the fault or whatever issue happened to cause the spike in the current is now safely extinguished. Voltage rating is, of course, the input voltage, around 480, 277, or 120, and that is the supply that you are bringing into your building. So how does a breaker work? Non-automatic manual operation is just using a lever to open the breaker. So as you see, the power comes into our terminals here. We will go through normally through the arc chamber into our fixed contacts. The powers then go through and the current flows out to your branch where your circuits and all the products download. When you flick the switch, you'll notice that our moving contacts pull off, which then disconnects the circuit completely from the power coming into the building. This means nothing down the line has any more electricity, there's no more current, there's no more voltage, and it's safe to be, you can use it to perform maintenance, or you can go and find out if there's any damage to your products down the line. Automatic means that you do not actually have to touch the breaker. Now, this is what we considered a very useful safety feature. And what we're showing on the side over here is your basic trip curve, which is a long delay and then an instantaneous delay. We'll get a little bit more detailed a little bit later in the presentation about these. Basically, what you see is on the x-axis is the current. This is logarithmic scale. So this is as the rated current, so 10 times the rated current. On a long delay time, you will have this much time, whatever seconds that may be, or milliseconds, as it were, before the breaker will automatically trip. Now, these are all settable, so I can push this curve out a little bit further, which would mean that I'll have a longer time at 10 times the current rating before I would trip. Instantaneous, again, is as soon as I see 100 times my current rating, I'm going to pop automatically. There's I believe a 2 millisecond time delay when we see this instantaneous rating. So some of the causes of this overload of this automatic current protection overload condition, that means that we have a load somewhere down the line that is just pulling an extraordinary amount of current, not what it's rated for, not what you want to have happen. This can cause danger in heating, it can cause fires, it can cause damage to your equipment, and it also puts your people into a dangerous situation. This is your first part of the trip curve called the L for long time delay. What we allow is for an instantaneous spike. So if you are at 10 times your nominal rated current, you can pull in, say, you have a motor or something that's a heavy current when you're going to get a real sharp spike in your current. You can go for a couple of milliseconds without tripping the breaker. This is normal use. You'll see that on big turbines and motors, but you won't trip the breaker. However, if that load keeps pulling that amount for a longer amount of time, that's when we trip. So during the overload, the excess current will go through the breaker and generate heat. The greater the overload condition, the greater the heat, the higher heat, and we trip it. How does this work? Well, what we have is called a bimetallic element placed into the breaker. This has two different metal alloys in it, very proprietary combination. We can't tell you. We have to make sure that you sign an NDA. And basically, one of the metals will expand quicker than the other. This causes a deflection in the element. That element bends, and you will see that it trips. Again, if you look, the heat is heating up those bimetallic elements right down here in the box. And as they get hot, it bends and it opens or moving, therefore disconnecting power down the stream. So if you have one of your loads that maybe is misrated or is starting to pull too much current, you don't want to get too hot, and so that this this mechanism will trip. Again, you have a long time delay because there will be spikes in the current on certain loads, especially inductive loads, and we allow for that spike to come in as long as it's a quick spike without tripping it. The second one that's most important is the short circuit protection, I like to call it. It's an excessive current condition when the phases make contact or you have a short to the neutral or ground. Correlates to the second part, which is called I for instantaneous, and these trip curves are pretty much across the industry standard. So you'll typically hear an LI, sometime an LISG, and these are just different portions of the trip curve that tell you what fault and how long it takes us to trip and open the breaker. During a short, the current can flow 1,000 times greater than the normal operating current. So I think if anybody's been in the industry and has ever touched phase to neutral or two phases together, you see the big spark and everything pops. It is instantaneous. Well, that's kind of a misnomer because we do have about a 2 millisecond time delay before we actually trip. And that's just the nature of the physics behind how we trip using the magnetic fields that we are sensing the current going through. So this magnetic field, again, is going to be in here, and what it does is it requires this plunger, which is basically just a metal rod inside of an electromagnet. When the magnet starts getting charged, it's going to force the plunger down, which then again moves the contact out, opening the breaker. So I don't know if you can see that. That happened rather fast. That's why it's instantaneous. It's not a warm-up of the metal. It's as soon as the induced magnetic field is there due to the overcurrent, which is very quickly, the plunger shoots out, pushes down our movable contact away from our fixed contact and out, and we kill power down the line. You notice that it all goes through this arc chute because as that current's going through and these two contacts pull apart, you will see an arc flash. Again, when our arc chutes are designed particularly to deionize the air that's around it, absorb the energy without much damage to any of the contacts or any internal workings of the breaker. The other curve that I mentioned just before was the S curve, so this would be considered an LSI curve or an LSI breaker, and it stands for the short time delay. So again, this is for when you know that you're going to have an instantaneous spike because of the load, whether it's being inductive, high resistance, it's going to spike. But again, you want a little bit of a time delay because you know that every time you start that motor, you're going to see the spike. If you didn't have this time delay, as soon as it hit the instantaneous level, it's going to pop. Right about here, you can see that you're going to absorb that large spike, and you'll still be running perfectly fine without any interruption of service. It's typically used in the selective coordination applications, and that basically means if you have more than one breaker, so you have a main breaker, and then a branch breaker, and then a feeder breaker down the line, if you select the S breaker at the closest to the service at the longest time, it can absorb a large spike without popping. Then as you get closer to your equipment, you're going to make the time delay a little bit shorter and shorter so that when you do have that fault, it happens quickly at the breaker closest to your equipment. So then you're not shutting down the whole entire branch, you're just shutting down that breaker that is by the equipment. This saves a large time on startup and shutdowns, and in an application such as the mines or any place where you're doing a high yield over time, even blowing a branch and shutting down 3 conveyor belts is a lot more expensive than just shutting down the one where the fault happens to be. So the automatic means, you're going to see a lot of these curves all over the industry. As you notice, you have 3 curves. In this one example, you have the L into the I, here, here, and here. Our breakers allow you to choose which curve you want to employ. So even though you have an 800 amp rating, you may want to have a shorter time delay on an incoming current. So you would choose this L curve and this instantaneous so that when you hit the spike very quickly, it's going to shut off. However, if you know that the spike is going to be coming and you need a little bit more time to let the spike cool down or get to the motor so that the load warms up, you can pick the long curve over here, and you can see that your operation will keep on going at this spike for a longer time before the spike actually reduces itself, and then you'll keep on running for the life of the circle. You can actually set the different levels for the L and the I based on, you know, whatever you choose. So you can choose an L curve that's way up here, saying that I'm going to have a long time delay before I have to trip, so I can take a lot of current in an overcurrent situation, but my instantaneous is going to be either here or here, so that as soon as I get past this instantaneous, I'm braking. But I'm going to allow this long time delay at this current level. Now, if I didn't want to trip that early on an instantaneous, I can choose this instantaneous on the same long curve. So you still have the luxury of getting that spike here. The spike can come down, you'll be in fine operation, but once you hit this instantaneous, it then pops. So again, this is very useful when you're doing selective coordination, but it's also useful when you understand the application you're in, the loads that you're seeing, and the actual current form that you're going to be seeing, whether it's a large spike, long time delay on the current draw, or if you're going to be seeing a choppy current time and time again. A maximum interrupt in grading is the maximum current level the breaker can safely interrupt when applied within its rating. Basically saying that if you go 1,000 times the current rating of this, say 800 amp breaker, if you go past that, we're going to open instantaneously at the 2 millisecond mark right here without any damage to our breaker. However, if you go past that line, we cannot make that same statement, because you are exceeding the maximum current level. This is something you don't want to do because it can result in catastrophic failure in both the breaker and the equipment down the line from the breaker. So as you can see, it's very important as you are looking at these breakers and speccing out these breakers to know exactly what load and the application you're looking at. Again, if you're looking at a spike, you're going to employ the L, and then you're going to make sure that your time is fine before it levels off, and hopefully your current stays below the instantaneous. Goes above the instantaneous, we're going to open right away, and if you go past even our maximum rating, then we're all in trouble. So it's very important to look at the ratings, both the voltage ratings and a maximum current level. Generally, I like to recommend you want to stay 80% below or 80% of the maximum current rating. So if your normal rating, if your normal current is going to be around, say, 800 amps, you would pick a 1,000 amp breaker, and then you will be running safely below this mark on your breaker. So some product fundamentals. When we get to this arcing, you can have a high let-through of energy. I squared T is the levels that can result in thermal damage. This is more of the arcing. So if you think about it, time can be low, but your energy can be high because I is squared. This is the square law of the current coming in. This is going to cause thermal damage, mechanical stresses. Basically, the challenge for the breaker is to make sure that we extinguish the time as quickly as possible, therefore letting the let-through energy as low as possible. Let-through energy can get past the breaker because, again, these things happen very quickly, and it can cause all sorts of stress down the line. So magnetic forces are created. This can cause bus bar bending. This can cause wires. I don't know if anybody has ever seen high voltage wires that are having issues and they kind of bounce around like snakes. What we want to do is we want to stop that, again, for the safety of the person and for the equipment. UL turning limiting substantially limits the peak let-through. So UL has a standard that says we will not let this go through at this much energy go through at this time. This means less than half a cycle of the input. So as everybody knows, power coming in comes in as a sine wave. You have a positive cycle and a negative cycle. It has to be left at less than half the cycle. They do not want to see a full wave go through with this energy because your time is double that, which really increases the amount of energy that's going to be seen down the line. Typically, our breakers do it in a quarter cycle, which is usually a little bit better than the industry average. So we do limit that current, we limit that energy, we cause more safety down the line. ABB has UL current limiting breakers and the T-Max and soon to be the T-Max XT breakers. And basically we use those for feeder devices in UL 508 control panels. It's for the sensitive loads. So if you think about data centers or anything where a high peak or high energy, a spike in current, any kind of voltage spike, it can cause damage to these, which is costly, time consuming, and not the easiest to repair. Using breakers in the right way with the right settings for the trip curves, and if you do coordinated selective coordination, which is using the right breakers down the stream, you can reduce the amount of damage, the amount of downtime, and the amount of maintenance that is required on your equipment. Plus, you're also getting a very higher level of safety for all the people that are involved maintaining that equipment. As we alluded before, selective coordination minimizes the effect of the electric fault, ensuring that the breaker closest to the equipment is the first to pop. So in this typical example, you're going to have a large breaker that's taking in the power from the utilities or from your branch. We have a secondary that might have a couple of sub-branches coming off, such as the T1s going over here, where you have only 125 amps coming in, and maybe you have another one at 125 amps. Now, if this load down here has an issue, you don't necessarily want to take out the main breaker, because when you do take out the main breaker, you are shutting power to all the equipment down the line from there. So you can have several different engines, turbines, conveyor belts, what have you, coming off of that breaker. You don't want to stop 5 lines because of a fault on one. So you would choose lower breakers and put them closer to the load so that if one conveyor belt has an issue, only that conveyor belt will pop. As you can see, they're setting the trip currents so that the one closest to the load, closest to the conveyor belt in my example, will be the first one to pop. So if I'm at, say, 1 times my nominal, you can see that T1, which is this tiny little breaker, that's going to be your almost your machine breaker, if you will pop before T5, the T5, which is our branch feeder over here, pops. This means that any other equipment that is coming off this T5 will be running just fine, and all you lose is the downtime from this one conveyor belt. We have several different configurations that you can mount the breakers in. We have fixed, which is a bolted connection, cable lugs and bus bars. Breakers mount into the equipment of the enclosure and will not be removed without de-energizing the system. Now, one of the big safety features that we have in our breakers is that we have an isolating wall, so that when you do take out the breaker, you will be shielded by a wall that keeps the live bus bars away from being touched. This is very significant because you don't want anybody putting their hands in there and being exposed to the service line. The currents there can cause real big problems. The other types we have are plugins. This is an assembly that requires quick change, so if you have any kind of fault or if you need to up the ratings or change the ratings, you can pop it out and pop in another devices. They're generally used for the T-Max breakers. These are field installable, no racking mechanism needed. Again, it's just a simple pop in, pop out. These are going to be the devices that you're going to see close down the line on the branch circuits that are going to be protecting your equipment. We have the mounted configuration of a drawback. This does require the racking system, which means that you have to have the breaker and a cradle, and you must rack the breaker into the cradle where the power is coming into. Again, this is where our isolation bolts are very important, because as you have your bus bars carrying the service 600 volts or what have you at an extraordinarily high current, this is something you don't want to expose anybody to. It doesn't matter how much PPE or personal protection equipment you are wearing. It's a very dangerous situation. So what we have is the shutter walls will keep you isolated until the breaker itself is completely racked in. So this is just a safety feature that we have on our breakers. It's widely used in critical power. So again, it's something that you don't want your power breakers to go down. You need that power all the time. Any second and any minute that you are losing power, you're losing money. And typically our customers don't want to have that. You can have it on the T4 through 7, which are a little bit bigger breakers than the small ones that we showed beforehand, a little bit bigger than these guys, and they have better ratings on that. You have a lot of different accessories that you can put into these breakers, which allow for a lot of different applications. An undervoltage trip is basically a coil that sits inside the breaker, and it has a coil that is monitoring the voltage that is coming into the unit. Now, as we all know, in the United States, we have typically clean power, but there are plenty of places that are rural that have power drops coming out of the service provider. And this can cause damage. If you have a 480-volt motor and you're starting to see 400 volts on that motor, you're going to really stress the windings of that. So what this allows you to do is set a level as to monitoring the voltage coming into our breaker. And when it dips below that, this shunt will recognize it and open the breaker automatically. We have auxiliary contacts so that there are ways to bring the switches to disconnect the breaker or open the breaker without actually going to the breaker. Again, a very nice safety feature. You can have it done on automatic, say a time clock. So on a building that you want to shut down the breaker on, say, a Wednesday at 6 p.m., if you have a time that can send out a 24-volt signal to our breaker, these auxiliary contacts will accept that, a dry contact closure, see that now you want to open the breaker, and it opens. This mimics the state of the breaker as well, so we can give you an output, and you can put on a pilot light, which allows you to know if that breaker is open or closed without actually going to the breaker. Again, one of the things here at ABB is we believe safety is our #1 concern, and we're making sure that nobody's going to go into a live breaker situation unprepared and not knowing what they're getting their hands into. Our shunt strip is also available. It's field installable, so you never have to go towards the service power. You can actually take off the face of our breakers, and you can use these low voltage breakers, shunt strips, and what have you to add more product features and fundamental applications can be covered by the shunt strip. So basically, as soon as you flip a switch, the shunt will see the current go through and open our breaker. A bell alarm, again, field installable. Basically, it just lets you know the state of the breaker so that if you're in a remote area, you can hear that the breaker opened and know that the power has been cut down to whatever branch, main, or feeder that you have seen down the line. Again, trying to remove the aspect of anybody going towards the breaker, using the breaker without having the proper, suiting up into a PPE that requires a half an hour, sending a guy out there. We want to make it so that you can remotely tell what the breaker is doing, and we have trip units that actually can tell you why it did what it did. So some of the applications that we have. The UL standards, UL 489, this is the low voltage MCCBs, molded case circuit breakers, and ground fault interrupters. These are for service enters, feeders, branch circuits. It's in accordance with the NEC, the National Electrical Code, and it covers instantaneous trip breakers. Basically, when you're using anything with power and you need a breaker in there, the motor controls always have to have breakers by the NEC. These are the MCCBs are what you're going to be using in your switch gear. We have 100% rated circuit breakers, UL 489. It's unique, which means you can control the loads, which is typically not an application that's recommended for opening and closing that load. So generally, I know it's not the right application, but a lot of people, as they leave their building for the weekend, they want to flip one switch and have everything shut down. These circuit breakers can handle that. It is intended for no more than 80% of its rated current. Again, you don't want to press, that's the guideline I spoke to beforehand. Generally, you want to stay within 80% of the rated current. You don't want to push things to 100%. It'll work, but it's not the safest. It's not the safest way to use the product. Special label is required for thermal testing. We have this available at the T-Max 15 amp to 3,000 amps. So 80% of 3,000 amps, you can be switching under full load a lot of devices. It has a very small frame size for the breaker, which reduces your panels, so you no longer have to have a huge panel in order to control these loads for safety and or just on-off toggle. And we also have smaller conductors. That means less copper, less wires, and a lot more movability. You can get your hands in there to actually attach the conductors to our devices. It's a very big thing for your contractors out there when they have to go and wire these devices into their systems. Another UL standard that we are for is the UL 1066. This is power circuit breakers. Now these are really the heavy duty type breakers. They're for installation in the switchgear and switchboard. This is where you're going to have your draw out or your fixed, and it's intended to use with specific adapters or receiver. Typically, you're going to see a cabinet like this that's going to be on your main branches, and these big circuit breakers are going to be controlling different branches going out with those tiny molded case circuit breakers, having the actual feeders to your machines, maintaining the safety and the reliability of the electrical service that are going into the building, out to your branches, and then eventually out to your loads. UL 1558 low voltage switchgear is another UL standard. It contains low voltage powered circuit breakers, switches, instrumentation, and metering, which means that you can see how much voltage is going in, you can see how much current is being used. And I know out here in California where I'm based, it's going to be a huge thing as we get into lead points, Title 24, California Title 24, and eventually the Net Zero Initiative, which will be taking place in 2016. So it's important to know what kind of current, what kind of power, and what kind of voltage you're seeing going into your equipment. There will be rebates based on that, and there will be some kind of punishments, or I guess they call it overage charges when you're using too much power at the wrong times. Service providers love this type of stuff because it allows them to know what kind of service you need, when you're going to be hitting it, and you can report back to any issues that you have. The UL 891 switchboards are large dead front panel, rated for 6 volts or less. This is a little bit less on the power side and more for the critical powers. Basically, it looks like a nice little cabinet with a bunch of switchboards feeding out to all your different equipment. You're going to be using, again, these little T-Max breakers that we have. This allows you, if you do the selective coordinations and your studies properly, to make sure that the breaker closest to the equipment pops first, reducing downtime, reducing cost, and reducing maintenance. This is used in just about every application I can think of, where you have your main breaker here. That's this Emax, which is a huge breaker that's bringing in all the power into there. We break it out into feeder breakers, and then eventually down to your actual branch breakers. Some more applications that can be covered with all these breakers are the UL67 panel boards. And these are devices that convert incoming electric power to smaller circuits. Again, this is overload protection or short circuit protection. They're the high-end fuses. So if you look down here below, this is the NEC requirement for a motor load. So you need to have each one of these devices into the branch leading up to a motor load in order to comply with NEC code. Luckily for us, our breakers do have all these built into them right up to here. So you have your overload, you have your short circuit, you have your disconnect means. So all you really need is a controller, which can be supplied with a motor control unit and an MCU. It can be a simple contactor if you want. And then you have a local disconnect switch, which could be a T-Max breaker, those little breakers that we talked about. You can wrap all this into one simple cabinet that can run several different motors, meet NEC code, and still be UL67 compliant. Industrial control equipment is usually what we're using this kind of equipment for. It's starting, stopping, regulating, and controlling electric motor loads. So you really have a lot of power in this little cabinet here. And as we all know, motors are a big investment. So you can have a $40,000 motor where if an undervoltage hits it and your windings go, that's going to be a lot to replace, not to mention your downtime. A simple product like this with our MCUs, these are our motor controls down here. We have a breaker right above here, complies with the NEC rules, UL67, and it will make sure that your operators and your equipment remain safe throughout the lifetime of the product. So as we talked before, the motor circuit control right here is all inclusive into our T-Max breaker here. So this is a typical setup that you're going to see where you have the disconnect and the short circuit. So this is providing that the LISG curves that we talked about earlier. The power is coming in here, so we're looking for any problems down the line with this motor. Catastrophic problems. So winding breaks and you're starting to short. You're dropping neutral. Somehow your two phases get caught, and believe it or not, I've been out into Arizona on the surface mines, and they talk about all the wildlife that seems to creep into this cabinet, and everything's fine until they cross over phase, and then you need this to make sure that your motor doesn't pop. Right below it, you have the actual controllers. These are the MCUs. Now we have several different type of motor controllers which allow you to do slow ramps, quick ramps, kick starts, all different profiles as far as what your motor requires, torque control, voltage control. So our controls are really, again, a topic for another webinar, but they allow you to comply with the NEC and, believe it or not, extend the life of your $40,000 motor. Voltage case switches, different than a breaker, because the switch is just going to open and close, is also required as a disconnect means above it. It does not provide overcurrent, overload, or ground fault, so you don't have the I protection that we talked about. You don't have the L protection that we're talking about. It enhances, it can be enhanced with the shunt trips so that, again, you can see an overvoltage and pop this. But this is the guy that sits at the very beginning of the chain. So again, if this motor is having a problem, what you hope to happen is that your local disconnect will open it up and cause safety. If not, this overload will see the problem and open up, saving everything back. But if all else fails, you're going to need this disconnect means, which means I have to shut down this whole branch to make there's something really wrong, and I'm going to have to trip to make sure that the current that's flowing through me does not get to my motor or anybody down the line from that short. Some breaker basics on the electrical standards. Now we're going to talk about IEC. IEC 60947-2 is the low voltage switchgear and control gear. This standard applies to the circuit breakers, the main contacts, which does not exceed 1,000 volts or 1,500 volts DC. That's right, the breakers can not only do AC, we also do DC. Again, the DC is very important when you're talking about motor controls. And we cover all the bases with our full line of breakers. Applicable standards, we're not just located here in the United States. Most of the industry is also complying with CE, which is the European UL, if you will. Triple C, which is the China UL, if you will. Most of the time, if you have UL, you're already cleared in all the North American markets. They do carry a CUL as well, which is for the Canadian market, and NOM, which is NOM for the South American market. So that was a quick overview of the breakers as a whole, their functionality. I didn't really get into many of the specifics on the products. We can always, if there are comments, if you need me to come back, I could do another one with just you guys. I believe my email's out there. So if not, it is Edward, EDWARD, Uftring, U, F as in Frank, T as in Tom, R as in Robert, I as in Igloo, N as in Nancy, G as in George, at TNB, that's Tom, T, Thomas, N, Nancy, B, board.com. So I will now open up to any questions that you might have once I find out where my question is. I have a lot of questions, apparently. Okay, let's see what we got. Is the maximum enter rating a symmetrical or asymmetrical rating? By John Martin, it is a symmetrical rating. So we do not do asymmetrical ratings. An can you explain what you mean by electronic trip unit? An electronic trip unit is a trip unit that sits onto the device. We have dip switches that allow you to set the LIS, but also you can plug into the electronic trip unit and give the through an eKIP software program that allow you to set all these parameters up with your computer and move on. 2 milliseconds, how many cycles is that before the breaker opens? 2 milliseconds is a quarter of a cycle. So it's not even the half a cycle that UL requires. It is actually less than that. It's half of what UL requires. Does the breaker short circuit condition include phase to ground shorts in addition to phase to phase? We actually have a separate protection for that. It's called the ground protection. So you will hear LSIG. The G is phase to ground. You can get that on all our, not all of our breakers, but the Emax breakers will come with that identification so that you can, yes, have a fault that will look phase to ground shorts. Maximum current rate interrupting rating. So again, this is the most current that our device can stand open and not cause any damage. So after we get above this maximum current rating, so if I have an 800 amp breaker in there, if I see 900 amps, that's above my maximum current rating. That means you can see damage in both the breaker or it cannot function at all and you can have fusing of the contacts. My short circuit is 40 Ka. Will it be okay? Yes, it will be okay to use a 42 Ka related breaker. The recommended gap between coordinated curves is actually up to the coordination study that you provide. We can go very small. I mean, it could be within, I want to say like 0.1 amp, I believe, all the way up to 10 times. So we don't want to recommend what your distance, your gap is between the curves, just simply because it depends on how much and how much safety you want to provide into that branch circuit. What is the optimum number and rating of spare breakers to be recommended for a new installation? You know, that really depends. The ratings depend on what your application is calling for. The spare breakers, we usually do not see the need for a lot of spare breakers. We do quality checks at the factory before they go out, so each individual breaker is tested under load, and we know that it is okay. Some of the standards practice is usually you carry about 10 extra breakers because if you're blowing through more than 2 or 3 breakers on a job, typically there's something really wrong with that job. Again, the breaker should open before it gets damaged. In slide 3, showing 3 breakers, instantaneous time look longer for larger breakers. Is that the case? It all depends on what you set it up for. So a larger breaker can have a quicker time, or it could have a smaller time. The rating of the breaker is not actually indicative of the time delays or the curves that are being shown. What those curves depend on is using the trip unit, which are either dip switches or electronic trip units. You can set how far and how long you want that time delay to be and what actual trip protections you want to activate. So in an LSIG breaker, you can actually shut off the instantaneous and just use the L, the long delay settings. So, I mean, it really, for that, it's up to, again, the application that you're using, and in the studies that you use, it should really fall out of that. What is the typical setting for undervoltage setting for the trip main breaker and feeder breaker? I've seen it at 5%, and I've also seen it at 10%. There are some critical powers, if you're looking at hospitals, where they actually try to dial it down to 1% of the voltage. To me, that gets a little bit hairy, because you could have the switchover happen very fast. You know, a big storm rolls by, you'd see a 1% dip, and then all of a sudden you're tripping. So I would recommend around 5 to 10%. As an individual component, does an MCP have a short circuit interrupting rating? Not as an individual component, it does not. There are no fusibles. That's why we have the breaker on top of the MCPs. Those are going to be your short circuit interrupting rating. So the SCCRs are not going to be there. How are your breakers locked out? How are your breakers locked out to meet OSHA requirements when servicing equipment? We have several different options. You can actually have a lockout tagout system. We can come with the accessories where you can make sure that it's a lockout tagout electronically. On our new breakers, you can set it up for a lockout tagout as well. So OSHA requirements will allow a test and we also have a test and maintain position for the breakers. Basically, in the test, you're racking out the device and you're taking it away from the service, but you're still allowing 120 volts so that the breaker acts normally. As far as when you're servicing the equipment, when you rack it out completely, the only thing you're seeing is 24 volts DC to power up the internal electronics of the breaker. There is nothing going on as a high power. What is the typical operating time for breakers on an overload trip? Again, depending on what overload you're looking at, you can set that time delay on the long for whatever you have. Typical, what you're going to see out in the field is in an instantaneous. You're at about around 4 milliseconds. Again, we can do it at 2 milliseconds. It really depends on the breaker that you're using, the overload, and the rating that you have set. So each plug, each breaker can have a rating plug stuck into it. Depending on that rating plug is depending on how we're going to be looking at the overload. We have several curves. I can get you the information on that. From there, you can actually see what we do as far as the time. So again, the electronic trip unit, there's some confusion. A trip unit is basically the unit that you put into the breaker to set those trip curves. The long time delay, the short time delay, the instantaneous time delay. An electronic trip unit, instead of just using dip switches, you are able to plug in with a computer, and you're able to set that so that it uses more granular. So on the dip switches, you can do it in multiples of your rating. I believe it's 20%, 40%, 60%, and 80%. Since you're limited by the dip switches, you could do any combination of that. However, the electronic dip switch, when you plug in, and we also have a Bluetooth module available, so you don't even have to go to the breaker, which is a huge safety benefit. You can set it down to any 0.5%. You can go to 0.675%. You can set it to any level that you want. So it gives you more accuracy in your coordination studies to go ahead and limit the current that you're putting in. The two curves in the L and the I is available because you are able to set one unit to have two separate curves. So you can have an L1 and an L2. This allows the breaker to, at some points, be set to a lower time delay when the L1 is activated, or you can set it to an L2 so you can switch the, if you will, breaker profile so that L2 has a larger time delay. So the ground fault protection, basically what we talked about is a short. When you see a phase to neutral or common, or a phase to phase short, is when these voltages come together. Ground fault is when the electronics are actually leaking current to ground, which is a very dangerous situation. We do have a separate separate curve, and we have separate units that actually do ground fault. This is not like the GFCIs that you see in your house, where at 500 milliamps it measures and then it opens up to protect you. This is actually kind of looking at the current, and as soon as there's an imbalance in the phase, which means that that current is going, instead of from phase to the return, it's obviously leaking somewhere. That somewhere generally means that current is leaking to ground. At that point, we give you a margin of how much do you want to leak to ground, and if you exceed that margin, we consider it a ground fault and we open the breaker. The earth fault settings, again, I talked about the LSI curves that you all saw. Our breakers, if you get a hold of our literature, and I can make that available again with emails, I can blast it out. Basically, it's another curve where you can set the rating of it as well as the time delay of it. Generally, you want that as quickly as possible, because if you're leaking current to ground, if you're not getting that current back on the return, that's a dangerous situation. That means it's going to be energizing something it shouldn't be. So you can, again, just flip over the dip switches in your settings, move the curve to where you want it to be, and you can actually do ground calls. Yes, I do make house calls as long as you're in the West Coast. I cover the pretty much the 12 states that are west of the Rockies. Other than that, I will direct you to the CES in your area, and he and or she will make the ground calls. The I squared T is basically the let-through energy. The question was, can you please explain the I squared T feature on the MCC B again? So I squared T is power. It's basically, you're going to see how much power energy is going through the device. Current limiting devices make sure that the time is reduced such that the power is reduced. So the I part of the I squared T is something that we can't control, right? The short circuit's going to come in with whatever amount of power, current it's going to have. What we can do is mitigate the time that it takes. Again, going down to 2 milliseconds, we're saving you almost half the amount left through energy. So, you know, you're not going to see a huge amount of power coming down the line since we cut it in half. Most people use 4 milliseconds, which doubles. Again, you're looking at 2 milliseconds for T rather than 4 milliseconds for T. So we half the amount of let through energy, so half the amount of energy that anybody can see down the line from that MCCB. Accounting for XR ratio, can a breaker be returned to service after? Yes, it absolutely can. So our service, we have our own services. A lot of our partners in the business also have services. Our services can reset it, even if there's the interrupting at its full rating. We can do services on the contacts. We're unique that ABB can do services as far as the arc shoots as well. So after your arc shoots, you want clean arc shoots, we are able to go out there and clean it. Basically, our service guys here almost make it brand new. I've actually been down to the Ahelia factory. I've cleaned out the breakers myself, and it's really hard to tell the difference. They remove a scarring, any kind of pock marks, and if you have any issues with the product itself, they will fix it and give it back to you almost like it's brand new. Let through energy again. So if you think about current times time, that's the wattage that is going to be coming through any device or down a line. There are two ways to limit that. You can limit the current that's going to be going down the line, therefore reducing it by the square law, or you can reduce the time. Since we are not able to reduce the current because we don't know the nature of the fault before the fault happens, what we look to do is mitigate the time in which we open. So we cut our let-through energy by half by making sure that we're doing it in a quarter cycle rather than the UL demanded half cycle. Why do circuit breakers not have a means to attach a lockout block? They do. You can order it. All of our breakers, again, I didn't do this product specific. If you guys are interested in ABB products specifically, we can talk about all the accessories. We have plenty of lockout tagouts. We actually have electronical lockout tagouts on our new breakers as well. Series rated breaker is a little bit tricky because when you're doing a series rated breaker, to get the ratings you actually have to run the test. So series rated breakers don't come out with a series rating. We do have a comprehensive list of all the tests that we have. So there are part numbers. We tell you exactly which series are rated and how they're rated, and the D rating as well. That will be on the website, and again, if you can't find the information, any CES or application engineer at ABB will be glad to help you with that. When do arc fault breakers require? So arc fault by the NEC is just brand new. It's coming out in the 2014, which will be probably enforceable by the next year, depending on the state adoption of the NEC code. Right now, I'm not sure what they're requiring, but the arc fault breakers are. Arc fault is becoming a very hot topic. We have separate units that do the arc fault. They're not typically found in the breaker. It is a different device that is set in the cabinet with the breaker. What they are using is actually optic feedback. So we're looking for the flash of light because it's the quickest. Light speed of light is as quick as we can go. And using optics and fiber optics back to a unit, that's how quickly we can open ours, extinguishing the arc as quick as possible. Again, another presentation. I will work with Nicole at EasyPower, which I want to thank very much for putting this all together to get more topics out to you guys. I believe it was useful. So arc flash is definitely a hot topic and something that I want to talk about. In the utilities at the power production side, the breakers are controlled by different relays using two CTs. Why breakers are not built containing controls within themselves? It's a space concern, actually. Our breakers actually have the CTs in them. We have a reduction side with our new Emax 2 breakers where you can put the control up there, but typically you don't want the controls coming from the breakers because of the stress of a full load being turned on at the breaker. Every time you turn that breaker on, those contacts, the bimetal, and all the electronics inside see a huge surge as they're trying to get the full current. Especially when you look at inductive loads and you're talking about a current that is 90 degrees out of phase with your voltage, it can cause some havoc on the internal components. We do, however, have load ratings on our breakers because we know it's an application that is being used. There's some power plants that I'm already in conversations with, and our new breakers do have, I want to say it's close to 15 to 20,000 power cycles that you can do under full load. However, again, it's not what you really want to use as it stresses the breaker, and it's a lot harder to replace a breaker or to service a breaker than it is to service a switch, a disconnect switch, a contactor, or something like that. Current limiting, I'm running out of time. So current limiting really is achieved by using the magnetic field that's induced by the high current. We then pop immediately on our movable contact. Basically, we get the rating by going through UL and passing their test. If your panel is fully rated, does it mean that all circuit breakers, including the branch circuit breaker, must match their service interrupting current? So basically, when you're in your panel, the rule of thumb is that the weakest link is your current rating. So you can have an 800 or 1,000 KA breaker in that panel, 2,000 KA breaker in that panel, but if you have a 35 KA MCCB sitting in that panel is only going to mark up to the 35 KA for that MCCB. Now, as we discussed earlier, you can go through the series procedure and actually run tests to see what the actual maximum is on those two breakers together, but that's time consuming. And you have to go through UL to get the actual listing for that series. We do have a bunch of those lists up on our website. You can see it, but typically when you put any kind of breakers in, common breakers into a panel, it's the weakest link. The lowest rating is going to be the rating of that panel. Not all breakers now come standard with a maintenance mode feature. Not all breakers do. Our breakers, all of our breakers do. So the maintenance is a feature that we require just for the safety of our customers. I do not know of any of the other majors that are doing it at this point. Not with all of them. What is the maintenance recommendation for breakers? That depends on your usage of the breaker. So if you're using it in an application where you're doing full load switching, you're going to have to maintain it often. The neat thing about our breakers is there's actually an indication, like both you can get it electronically because we do speak Modbus, Profibus, and 7 different protocols. So electronically, it can kick out and tell you the status of the contacts, the wear and tear, and when maintenance is required. And on our non-electronic trip units, we do have a red lights that will indicate that the current is seeing a resistance that's not really expected, therefore maintenance is required. So the breaker itself will tell you when it needs to be done. I see it as a problem when you have the different manufacturing, since breaker curves depend on each manufacturer, we require from manufacturer with submittals. Do you see any problem with that? At ABB, I can only speak for us. We're very quick with that submittal. We have most of our trip curves up online, so you can download them. We do work with EasyPower, and we're working with them to make sure that all their products, when you do have an ABB product, that the trip curve can be found on the website or a link, so that you just have to click on it to find the trip curve for that. Can trip settings be changed while live on? Yes, they can be, but we don't recommend you doing it. The best way to do that is with an electronic trip unit so that you're not near the breaker flipping that dip switch. Have been told by fuse proponents that if a breaker trip, there is no longer covered by warranty and must be replaced. Is that true? That is not true at all. We have a 2-year warranty. It doesn't matter if it trips or doesn't trip. You can get breakers with counters on them so you know how often they trip. And again, we do have indicators requiring when maintenance is needed. What happens with a current higher than the nominal maximum current? Can the load be safe anyway after the breaker is damaged, destroyed? Yes, it can. So if you're going over the nominal maximum current, what we foresee is that our breaker is going to absorb the biggest punch and be damaged. Not the safest. You're going to may smell fire, see smoke coming out of the panel. Nobody wants that. But typically, your load down the line is going to be safe from any damage getting to it. I have an 80 amp 3-pole MCD breaker with FD 335K stamped on it. Then FD interrupt capacity, RMS symmetry amp, 2240, 65 KA, 480, 35 KA. Please explain these ratings and how they apply to the connected load. So the ratings themselves don't apply to the connected load. What the ratings are giving you here are for the different voltages. You have a different maximum interrupting rating. So at 240 volts, that breaker is only going to handle 65 KA. 480 volts, it's only going to handle 35 KA. At 600 volts, 18 KA. So as you're going up in voltage, your current has to go down. Depending on your application, so if you have 480 volts, then it becomes a maximum of 35 KA. So a lot of the breakers are usually universal voltage, so you're going to have one that's 240, 480. This example, you have one that goes from 240 to 600, but each one of those voltages have to carry their own current rating. Are all breakers bimetallic? Now the bimetallic is just one component of the breakers, and yes, right now the industry is pretty standardized on using the bimetallics for the long trip curve. Basically, it's the cheapest, most efficient way of getting those bimetallics to bend and popping out the trip. Can you explain using breaker curves how upstream breakers affect downstream breakers using series rated assemblies? I can. Again, that's a long answer, Larry, so if you can send me an email, I'll go over it, but in a short term, we looked at the, let me see if I could go back to that, selective coordination. So if you look at the trip curves that I'm just about to show you in selective coordination, as you can see here, we have E2, which is the power breaker at the top, T5, which is the middle breaker, and T1, which is the smallest breaker. We show right now 2 reds, 2 curves for each one, noting that on the E2 you can set this curve up for it, or you can set this curve up for it. So typically what you'll see is you'll choose one curve over here, which means that if I'm sitting at 1 times my nominal current, instead of tripping at the second breaker, it will never trip at the main breaker, it's going to trip at the smallest breaker. Again, selectively coordinating that I'm only popping this little branch. Now if I chose to use something like the second curve, the first curve, and the last curve, again, at 1 times the current, we're going to be tripping here at the first breaker. If we keep on going, then a little time later, if you're still at that current draw, you're going to trip here on the second breaker. And then finally, you will not be tripping on the main breaker. Again, what this allows you to do is keep anything this is one branch here. You could have several of these branches hanging off. 1, 2 down here, 3 down here. You don't want to affect this second branch, this third branch, this fourth branch, because the fault is happening here. So if I popped E2, if I just had this one E2 over here and I popped it right at the one nominal, then all of my branches go out. So that's why you want to use the selective curve, selective coordination, and use the proper curves for it. Yes, I can talk about the NEC and the 240.87. It's going to be another presentation. Jamie, please email me and we'll get you an answer for that as well. I'll also get my product manager for the ARC Guard to go in depth with that. Electronic trip unit and a relay. A relay just basically opens and closes. The electronic trip unit actually has intelligence built into it so that it's monitoring the Rogowski coils that we have in our breakers or the CTs, and it's making decisions based on the voltage, the current, and everything that it sees. The maintenance. And then where would you maintenance switch on MCC CDs? Maintenance switches usually are recommended on all of them because, again, shutting things on and off, you want to make it as simple as possible. One switch right by the motor so that the person who's actually going to be doing the maintenance on the motor doesn't have to walk all the way back to a cabinet, doesn't have to find the right panel or find the right branch to kill it. He has a switch right by his motor. He can flick it off and know that he's safe down the line. Thank you very much for the excellent presentation. Question related to Arc Flash. Again, we will do this. Is the circuit breaker has several years old, let's say 40 or something? The interrupting capability is kept constant, or how can it be rated by the years? So that's a great question. Generally, there are a lot of these old breakers out there. You can't really tell based on the years because depending on whether you're using a service that's really lower than its rating, you can go for 40 years and not have a problem. If you're never interrupting or if you're never having any fault issues, again, those contacts aren't wearing, it can go forever. Typically, we would see about a 10 to 15 years we would recommend you changing it out. It doesn't mean you have to. But the increase in the safety, like the safety shutters, the added communication, Bluetooth, and all that stuff just adds to the safety. So we recommend about 10 years would be a good time to start looking at a retrofill to put in a new breaker with the new technology in. My email address, again, is edward.uftring@tnb.com. That is EDWARD. U as in umbrella, F as in Frank, T as in Tom, R as in Robert, I as in Igloo, N as in Nancy, G as in George, at T as in Tom, N as in Nancy, B as in boy, .com. If there are no other questions, I want to thank Nicole and EasyPower very much for putting this all together. Again, I want to reach out to all of you and let you know that ABB and the CESs here are ready to help you with any education needs, specific projects, even better. Thank you very much, everybody.